and welcome back to SWeCdes. So this video is in continuation to the binary search series, and we are back with another easy problem on the lead code, that is search insert position. So this is very similar position that we did earlier for the square root x or the bad version, but with a little twist. I'll tell you how. So let's try to read this problem first. We are given a sorted array of distinct elements, yeah, and a target value. So we have to return the index if target is found. So this is basic binary search. You are given a sorted array of distinct integer and a target value, and you have to return the index if target is found. Otherwise there is a little twist. If target is not returned, then we do not have to return -1. What we have to do is, like, if target is not found in the array, then we have to return the index where it would be if it were inserted in order. You see, if target is not found in the array, then we don't have to return -1. We have to return the position where it would have been when it would have been present in the array. So we have to do it in an algorithm with order of log n runtime complexity. So we know that since it's sorted array, a binary search can be applied. So I will think how it can be applied. Let's try to analyze these examples. You see, this is the array of sorted integers, and we have target 5. So since target 5 can be found at second index, like 0 1 2 second index, then our output is 2. Now see, here we have the sorted array again, but the target is 2. So 2 is not present in the array, so we do not have to return -1. What we have to do is, like, we have to return the index where it would have been when it would have been present in the array. So 2 must be coming before 1, sorry, after 1. 2 should have been before 3 and after 1. So the position where 2 would have been is like 0 and then 1, the at the first index. 2 would have been at the first index. That means instead of 3 here we would have been 2, and then 3 5 6 would have been there. Okay, similarly, you see, there is another condition where we have a sorted array. And we have a target, and if you will see carefully, all the elements in the sorted array are less than the target. That means we cannot insert 7 in between any of these elements, so we have to insert 7 after 6. So inserting 7 after 6, that means inserting 7 after 6 means we have to insert 7 at position 4, because this is 0, this is 1, this is 2, this is 3. So we have to insert 7 at the end, after the array. So you have to insert 7 at 4. So let's try to analyze how we can apply binary search in this type of problem, and it is very easy because we have already done binary search and we have already seen a different perspective. So if you have not seen that video, please go and watch that video before continuing to this problem. So we have 3 cases. So how we can accommodate all these 3 cases in a single binary search, I'll tell you. So first, if target is found. So first case 1, I'll write it. Case 1, if target is found, yeah. So you see, it is basic binary search. If target is found, it's basic binary search. Let's try to analyze this. 1 2 3 4 5 6 7 8. So, and target is, suppose our target is 5. So what was our condition in the different perspective of the binary search? Our condition was f of x equals to x greater than equals to target. You see, x greater than equals to target. That means all the elements less than target are false, and all the elements greater than or equals to target are true. We just need to find the first true value, and this will be our target. This is very easy with the basic binary search. So let's try to do the other 2 cases, and then we'll write the code. So we'll have case 2. Okay, sorry. Yeah, we'll have case 2. If target is not found, but there are some elements greater than target, like this. Suppose take an example, same example. 1 2 3 4 5 6 7 8. Suppose your target, okay, let's erase this 4, so we don't want this 4. Yeah, suppose I have this array and our target was 4. Our target was 4. So if you apply the same condition like x, if you apply the same condition like x greater than equals to target, then what you will get? Let's try to analyze what we will get. We'll get false here, we'll get false here, we'll get false here, we'll get start getting true from the first element that is greater than target, because the element equals to target is not in the array. So we'll start getting true for the first element that is greater than the target. So if you get the first true value, that means either it is the index of target, or it is the first value greater than the target. So if it is index of the target, you see, if it is index of the target, this true value, if it is index of the target, here target was 5, here target was 5. So if it is index of the target, then we have to return this value. Otherwise, if target is not there in the array and this true value is corresponding to the first element that is greater than target, so it is index of the element that is first element that is greater than the target, that means it is our inserting position. Because where will you insert 4? I'll insert 4 after all this false value, because all these elements are less than the 4. Then we have to insert 4 after the last false value. So after the last false value, what we have? We have the true value. So that means we have the first element greater than 4 here. And we know that 4 doesn't exist in array, so we have to insert 4 in this condition. So our element would be something like 4, 5, 6, 7 and 8. Array size will increase by 1. So we have to insert 4 at this position. This is also good. We know how to find the first true value. So it is also good. It can be done by the basic binary search. Now let's try to do for the last case. Let's try to do for the case 3. We have case 3 as if target is not found. That means target is not there in array, and all elements are less than the target. That means what could be our input is like, we have something 1 2 3 4 5 6 7 and our target is 8. So with this condition f of x greater than equals to target, all these elements will return false. Yeah. So you see where we have to insert 8 now. We have to insert 8 after the last false. That means we have to insert 8 here at this position. But if you will define your low value to be here and high value to be here, as I discussed in the different perspective of the binary search, with our implementation, if true value doesn't exist in array, then low will point to the last false value. You see, low will point to the last false value. But in this case where last false value is at the very end of the array, that means we know that no elements greater than target are found. All the elements are less than the target. All the elements are less than 8 here. So we have to insert our 8 here. That means if you increase your search space till here, if you will increase your search space till here, and we know about only these elements, and if everything here return false, then we can assume this to be true. So what we have to do? We have to do a little modification, slight modification, that we will not initialize our high value to the n-1. We'll initialize our high value to n, and we'll assume that it's true only if all these n-1 values are false. Otherwise, if there are any true values here, then we will just have to find the first true value. You see, it's a very simple thing to understand. If everything returns false in the array, that means we do not have any insert position in between the array. We have to insert 8 at the end, and your answer could be your answer could be n. So this is 0 and this is n minus 1, n minus 1. Your answer could be n. So what I told you, always try to include all the possible answers in your search space. So our search space is represented by low to high, low to high, 0 to n minus 1, but this is not covering the one answer, that is n. This is not covering one answer, that could be n. So we'll increase our search space such as 0 to n, so that it includes all the possible answers. We'll have to include all the possible answers. Let's try to implement it. I guess it's pretty much straight. So let's initialize two values, low equals to 0, and as I told, to include all the possible answers in search space, will initialize nums high to nums.size. Yeah, then we'll do the basic binary search code. It's the basic binary search code, low less than high. So we'll calculate the mid equals to low plus high minus low by 2. Yeah, now you check the condition, that is the basic condition for the binary search, greater than equals to target. That means if target is there, in the array, this will return the index of target, and if target is not, then there could be two cases, like all the elements could be less than the target, then we have to insert at the end. That is why we initialize high to n, not to n minus 1, because n could also be our answer. Otherwise there could be one more case, like if target is not there in the array, but there are some elements greater than the array, greater than the target, so we need to find the first element greater than the target, and that could be our inserting position. So this will do fine in there. So high equals to mid, and then we'll have to do else low equals to mid plus 1. Yeah, now just return low. Yeah, you just have to return low. It's a basic binary search code, only this thing has been changed. Let's try to submit it. Let's try to run it. Yeah, it's accepted. Let's try to submit it. Yeah, it's accepted. So you see, this was the easy problem. If you'll see the tags, it has been asked in so many FANG companies and the product based companies. But yeah, with a slight modification of our technique, we can handle all those three cases, all these three examples in a single binary search, and it was very easy to implement. Hope you liked this video, and if you love the concept, then please do like, share and subscribe this channel, and please do share your valuable feedbacks in the comments.